All right, we're back with example number two.
Boom.
Transformations, okay. So we've got f of x equals 2x minus 1. Yeah. Ooh. Synchronized. That's like synchronized swimming.
Boom.
Squared, right?
And squared.
So
Yeah.
what's our parent function?
Yeah, so our parent function in this one is going to be our quadratic, y equals x squared, or f of x equals x squared. I actually think this is like one of my favorite parent functions. I don't know why. It comes up in all my examples.
Yeah. It's
a good one.
All right. Yeah, every year I get students like misidentifying the parent function. So I got to be a little bit careful, I think. Okay. So we start out, we already got a head start. You could pause the video if you need to copy this into your notebook, because that's the wonders of modern technology. Okay, so we're going to start with the parent function. Let me zoom in. Look at that. Okay, so that's our good old parabola. So we labeled the points and everything. Okay, so we're actually going to do this problem two different ways. The first way is in the top row. Okay, the top row.
Yeah. Okay. So this one's really interesting. So the first thing I do when I look at these types of problems is kind of see what is going on. So this one we can see that x is again inside the function is being multiplied by 2. So that tells us we're going to have at some point. Again, I'm still not sure. I'm not even getting to the what to do when part. I just need to figure out what is happening. So with that 2x there, is telling us that we are again compressing our graph horizontally, so it's being smushed inward.
Yep.
And that minus 1 tells us that there is going to be a shift to the right.
Yes.
So the question is which one to do when. And what we're going to show you, like Mr. Chu said, we're going to show you two different ways. In a sense, it does not matter which one happens when, as long as you know what's going on, which sounds kind of obvious, but we really want to be just think carefully about these problems.
Yeah. That's the thing, knowing what's going on. Okay, so top row, it looks like we decided, hey, let's take care of the horizontal shift first, right?
Right.
Okay, so essentially what we've done is we've taken the original function and evaluated the original function for x minus 1. Right, so we essentially replaced this x with x minus 1, right?
Right.
Okay, so that resulted in the shift to the right by 1.
Okay. Yeah, so all the x coordinates essentially just get bumped up by 1.
Okay, so like over here, like if I take this point, x changed from 0 to 1 over here, and over here, x got changed from 1 to 2. So yeah, increased by 1, right? Okay.
By the way, folks, I definitely think it helps, especially when we're just starting, to have a couple reference points. So in the last example, in the square root one, we just had those 3. On a parabola, because it's symmetric, and I have like 5 or so.
Yeah, and I think they'll see on the next step why it's real important, because it starts to get like hard to see what's going on. All right, so the next step is where we wanted to take care of the horizontal.
The horizontal smushing.
Smushing, yeah, horizontal smush. Okay, so what we've really done is we've taken the previous function, which is this right here, right? We've evaluated the previous function with an input of 2x, right? So everywhere that we see x in this function, we're going to replace it with 2x. Right? Okay, so we did that over here. So we've replaced it with 2x. Okay, so actually, let me label what we did. Okay, so this was from here to here was a horizontal, a horiz shift to right by 1 unit. Okay, 1 unit. Okay, and what we're doing now is we're going to do a horizontal compression by factor of 2. right? Okay. So let's all right, tell me
Yeah.
to draw here.
So the thing about the compressions or stretching is, again, the kind of quote unquote center of your compression is always the axes. So since we're
Okay,
squishing them
right here.
horizontally, we're pushing
Yep.
them closer towards the y-axis here.
Okay.
And that essentially just means that if we're cutting it, squishing it by a factor of 2 or smushing it half as wide, then all those x values on our reference points just get divided by 2.
Okay.
And
So
so this -1, comma 4,
okay, here, okay.
the top for going left to right, that's going to be now -1/2 or -0.5, comma
Okay,
4. Should still have the same y value.
because we're dividing the x value by 2.
Right.
Right.
By
Okay.
that
So let me
compression factor, if you
So
will.
this is here we're dividing that by 2. So this is minus 0.5 comma 4. Okay.
Mm-hmm. So, and then our y-intercept here at 0, 1, since that's already on the y-axis, if it gets smushed towards the y-axis, it's still going to be exactly what it is. So it's still going to be 0, 1.
Okay, because 0 divided by 2 is still 0.
Still going to be 0.
Right. Okay. All right. So let me put that point at the same spot. So that's 0 comma 1. Okay. Keep going.
Yeah, then the vertex of our parabola at 1, 0, well, that 1's going to get cut in half, getting pushed towards that y-axis. So it's going to be 1/2,
Okay.
comma
So
0.
1 1/2. So 0.5 comma 0. Okay. All
And
right.
our next one, 2, 1, will be cut in half to 1, 1.
All right.
And then likewise, that 3, comma 4 up there is going to be at a 1.5 or 3/2, comma
Oh, okay.
4.
Okay. So yeah.
Sorry, just going ahead.
All right. Okay. So 1.5 comma 4. Okay. All right. So there we go.
And that's going to be our final transformed graph. And I think one thing that might look weird to us is that, well, at the very beginning, we see like the 2x minus 1. So it makes us think that the thing should have been shifted 1. And now you have like, kind of, if I look at the vertex kind of as like our reference point, I guess.
Oh,
it started
right
off there, but it ended up at only getting pushed over 1.5.
Yeah, by 0.5.
Mm-hmm.
Yeah, so this didn't do what you might initially thought it would have done just at first glance.
Right, but I think in the second example, or the second method that we're going to show down in the bottom, this will explain why that works. But it essentially is kind of preview. It's a result of the fact that you're shifting it horizontally in addition to compressing it horizontally. So when those work together, things are not as they seem at first anyway. Mysterious. Ooh, spooky.
Spooky. All right. Okay, so we're going to do it a second way, right? So let me put a dividing line over here. We're crossing a line.
So in the top row, we did the shift first. So now we'll try the horizontal compression.
Okay, first. So we're going to compress first. Okay, so we're going to do horizontal, a horiz compression by factor of 2. All right, so I think, okay, all right. So we're going to do the same thing, right? Divide the x coordinates by 2.
Yeah, except this one is going to be a little bit easier because our parabola is nice and centered around the y-axis already.
Yeah, so it's nice and symmetrical. So I think I could do that with less thinking.
Yeah.
Or less brain trauma. Okay, so here. So actually, I'm going to go ahead and label them while we're at it. Sure. So 1 comma 4.
Yeah, that 2 4 turns to 1 4, 1 1 turns to 1/2 1, and so on. Nice.
And negative 0.51 and negative 1 4. Just dividing all the x coordinates by 2.
Boom.
All right, cool. Then I could kind of sketch this in.
Yep.
All right, so it looks like that. It got squished around the y-axis.
Right.
Okay.
Boom. So what we graphed now, this blue one, or the second one here, that's y equals the quantity
Oh yeah, yeah.
2x
Y
squared.
equals the quantity 2x. Yeah, and
Don't
it's
forget those parentheses, folks.
we got to be careful because we're multiplying the argument of the function by 2, or
Right.
replacing
Yeah.
x with 2x.
Replacing the input. Yeah.
It's the whole thing that's squared, right?
Mhm.
Yes, so we got to be careful. Okay, so all right, so we're there. All right,
Okay.
let's keep going.
So that was our horizontal compression, and now we have to put the shift in there.
Okay. If we're doing it right, we should end up at the same spot as we did earlier,
Right.
right? Unless we did the one earlier wrong.
Oh, that's true too. Yeah.
But yeah, I think we did it right. Okay.
I
So
don't know. We had this is how many videos have we done together so far, and I don't know if they trust us yet, but
I don't know.
hopefully they think that top one is right because we think the top one is right. So.
Yeah, trust takes time to develop. Okay.
Right.
All right.
Yeah.
All right,
and
what do we want to do here?
So we need to shift this thing over. And so if we think back to the original function, it said like, okay, 2x minus 1. So it makes me think that, okay, it's going to have to be shifted over by 1 unit.
Yeah.
And the way we do that is we replace the x with x minus 1.
Oh, okay. So if we okay,
this is where we run into problems.
Yeah. So this is where we get messed up. So we would think that it shifts over by 1, right?
Mm-hmm.
So if we try, we're going to try to do that. Is that what you're?
Yeah. Let's just see what happens here. Or
So
maybe we don't have to graph it, but we'll show it algebraically. Maybe
okay.
underneath.
So let's say we want to shift by 1. So really, what we're doing is we're taking the previous function, right? And we have to evaluate that for an input of x minus 1.
That would push it over to the right.
Replacing x with x minus 1. So if we do that, really what's going on is we're doing this.
This is where you're going to be careful with parentheses, folks.
Yeah. 2, we're doing this, right? We're replacing x with x minus 1, and just being real careful about the parentheses. So here's the problem, right?
Right.
So
if I were to quote unquote, let's ignore the graphing part right now. Let's actually like kind of just clean up our expression here for our function. If you distribute that 2 into the x minus 1, we're going to end up with 2x minus 2, or the quantity 2x minus 2 squared, rather.
Yeah, which is not what we want, right?
Right.
Yeah, because we're trying to get to this over here, right? The 2x minus 1.
Right. We're trying to kind of recreate that because that's what the problem's asking. That one up there.
Yeah, we're trying
this will not work.
Yeah, this will not work. So what do we actually have to do? We're not going to do this because this gives us the wrong thing. So let me kind of
right. So I think instead of replacing that x with with an x minus 1, the way we're going to correctly get 2x minus 1 is if I replace that x with a x minus 1/2.
Yeah, because when you distribute that 2, it's gonna 2 times 1/2 will give you
bring us back to 1.
The 1. Okay, so we really want to do this. Let me switch colors. Let's make it beautiful fuchsia color. Okay, so now if we distribute that 2, it's going to be equivalent to 2x minus 1 squared,
right, which is the correct
which is what we want,
trying to get, right? So when you see that, now you see where he put that purple 1/2 in, or magenta fuchsia 1/2. That's where you can see, if we go back to our final answer from the top row, this is where you see that shift of 1/2, not a whole 1.
Yeah, like we had, here, right? The vertex, everything shifted over by half.
Right.
Okay. So I'm not sure which one was easier, top or bottom.
Yeah, I'm not really sure either. One way I know that, and sorry, maybe we should finish. I don't know if we need to finish this one, but you're going to take now a shift of 1/2. You're going to take that bottom row middle graph right there and just push them all over to the right.
Yeah. So let's actually finish it up. That's a good point.
Yeah.
So what we're actually doing is, let's describe in words. We're doing horizontal shift to right by 1/2.
Right.
Okay, so let's hey, yeah, that's really kind of weird, huh? Because we're shifting by 1/2 here, but in the previous one we actually did shift by 1/2, but after getting smushed, it ended up being an overall.
Right, because the smushing pushes it back, essentially.
Yeah. Okay, but let's go ahead and take care of this horizontal shift. So I'm just gonna add 1/2 to all these x coordinates over here.
Yeah.
Like, so let's just kind of move them over by half, half, half,
yeah, negative
half,
1/2,
and half. Okay, so it looks like that.
Yep. Yeah, and yeah, so like you were saying, not sure which one's easier, but that's the beauty of math. This is definitely one of those ones that's do whichever makes more sense to you folks.
Yeah, I think that's a good final point. Neither is right or wrong. It's whichever one is makes more sense.
Right. I think one method that I've seen people do, or one strategy that I've seen people do, is to always factor out the coefficient in front of the x first. Like that's the first thing they do. They rewrite the equation.
Oh, okay, yeah.
You know what I'm
So
saying?
yeah. So if we went back here and as a first step we said,
yeah, just your first step, like, oh, there's a 2x.
Yeah. This is the same thing as that's the same thing as 2 times x minus 1/2. Okay, so that'll help you like visualize.
Right.
It's actually a shift of 1/2, and it is a compression of 2. So okay.
Yeah. So hopefully that helps you out, folks. Dealing with the combination of multiple transformations of our parent functions.
All right, and I think we'll stop here. I think.
All right.
All right, cool.